Hello, welcome to this 17th class. So, today we will be discussing on nickel enzymes. It is very interesting to know that how nickel plays some important catalytic roles. So, nickel plus 2 why nickel? So, there are some historical importance for this also for simple hydrolytic reaction. That means some hydrolysis reaction, and which is well known that nickel center can interact with some of the small molecules and that ultimately gave us some idea that out of 8 known enzymes we have, and 7 out of those 8 these 7 enzymes basically can interact with small molecules like carbon monoxide, carbon dioxide, methane, H2, ammonia and O2. So, there is a big list that all these small molecules can basically go and interact at the nickel catalytic site, and they basically involved the use, basically they are the product sometime, use and or production of these. So, these can be function as very good small ligands, and apart from that they are all gases, which is very important. So, ultimately what we talk about that this nickel, and knowing a very good information about the nickel related to its coordination chemistry. Most of the time explaining all these reactions we take the help of coordination chemistry related to nickel 2 plus. And at the same time when we talk about nickel 2 plus, and we know that the most important coordination site it can give it to you is a octahedral coordination site, and in some cases in some forced condition it can also give some geometry which can be tetrahedral as well as square planar. So, when you move from one particular geometry to the other, we get less number of ligands, and some of these ligands basically are bound to this particular center. And if we go for this tetrahedral and square planar geometry, suppose if you have nickel and in a geometry like these which are bound to 2 nitrogen and 2 sulfur geometry environment. So, initially to know this environment in the living organism, in these enzymes, in these metalloenzymes, what people can find out this corresponding effective magnetic moment. So, that effective magnetic moment in a 4 coordinated system always gives us some idea whether you have a square planar geometry or tetrahedral geometry, because we know that it can move from 0 to 2.84. So, you have 2 electron paramagnetism for a tetrahedral geometry and a diamagnetic environment in square planar environment. So, if we can have some range of this, say 0 to 2.8 mu b. So, at one end we can have this corresponding one is square planar and at other end is tetrahedral. But most of these sites related to that one particular oxidation state, what right now we are thinking is as a 2 plus, that means the nickel in plus 2 oxidation state, the most common one. So, if we get something, but if your enzyme in a particular environment, because all these particular donor groups which is coming from the different polypeptide chain, the nickel sitting inside is highly distorted. So, if you have a distorted environment, which is a distorted one, and we get somewhere a magnetic moment in between. So, that gives us an immediate clue that if we have some binding pattern, that means like that of your, if we just simply correlate to our center like single iron rubidoxine. Single iron rubidoxine was, you have S, 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 S. So, but here it is N2 S2. So, and if the numbering scheme is such that these are short spanning one and these are also short spanning or the rest, that means NS, that means the number sequence in the long polypeptide chain, that means if it is 88 it is 92 or 96, similarly if it is 32 it is 36. So, this particular part we can consider as a part from the bidentate ligation. So, if this one particular plane and these two particular planes, if they are coplanar, that means they are in the same plane, we get a square planar arrangement, and if they are perpendicular to each other, we get a tetrahedral geometry. So, these two, that means how you can correlate these two geometries, we can introduce some parameter which is theta. So, when theta is equal to 0 degree, we get one arrangement, and when theta is 90 degree, we get another, and in between we get. So, depending upon its magnetic moment, suppose you are getting some magnetic moment is 1.4 and 1.6, you think that is a 4 coordinated geometry and it is intermediate between square planar and tetrahedral geometry. So, that gives some immediate clue how the environment is there and how we can identify the nickel within the that enzyme system. But apart from that, if it goes, because the nickel depending upon your typical corresponding potential, the E0 value, it can go to 3 plus or it can reduce to 1 plus, whether some redox catalysis is operating or not. And like your nickel in bivalent system, this trivalent nickel and monovalent nickel both are paramagnetic also. So, you get corresponding magnetic moment for identifying these, and also these two, nickel 2 is not, but nickel 3 plus and nickel 1 plus would be EPR active. So, these are the basic requirements or the basic informations what you can have to identify nickel in a particular center. So, handling all these gases, what basically contribute to the system is that they definitely play some important roles in the cycles of carbon cycle, nitrogen cycle and oxygen cycle. So, they definitely contribute the what are the nitrogen based species you can have in the environment, what are the carbon based species you can have in the environment, and some of these oxygen based species also. So, one such example, so out of all these different molecules, one is very important, is urease, which produces ammonia. Through hydrolysis. So, it is a hydrolase type of enzyme, and it was the first enzyme which has been identified long back in around 1926. One person with James Sumner initially was working with urease, and he could crystallize it. So, crystallization was very important. Crystallize it from jack bean. So, that crystallization in that particular time, that means is 1926, but he has no idea, no clue related to its corresponding property, but the crystallization of protein. So, the crystallized form, and which is metal bearing protein, at that time it was not known. So, he could crystallize some protein at that time. So, crystallization of protein was so important, because nowadays we know for determining the actual structure, we should go for corresponding protein crystallography. So, the discovery in that period that it can crystallize something and the metal was there. So, this crystallization was definitely dependent on the presence of metal ion. So, some protein environment, and if you give metal, because sometimes the apoenzyme, that means without the metal center, it is very difficult to crystallize. So, all the metal enzymes and metalloproteins are easy to crystallize at some point. So, the nickel bearing thing which can be easily crystallized, and it basically giving something which we can go for the corresponding crystallographic pattern. So, that basically earned for him the Nobel Prize in 1946. You see the time scale. So, after 20 years he got the Nobel Prize, not only for doing anything, but only for crystallization of the protein. But it took several years until 1976, only until 1976, because at that time, during the period of 1926 or 46, the analytical techniques were not so good, such that you can examine or you can characterize this particular urease as a nickel enzyme. So, that was our limitation. So, analytical techniques, even the crystallography, analytical techniques did not allow to be recognized this particular species as a nickel enzyme till 1976, but the reactions were known. That means, what it is doing nothing but a simple hydrolysis of urea molecule, producing one particular compound. One end of the NH2 group is getting hydrolyzed, producing one ammonia molecule, producing a carbamic acid. because we know that ammonia, then different amines and all, very easily we get the carbamates, and when we react with some ammonia or amine type of molecule with carbon disulfide, we get also the corresponding thio analog as dithiocarbamates. Xanthates are also like that when you go for those reactions on alcohols. So, xanthates, dithiocarbamates and the carbamic acid. So, in the second step, another molecule of urea is coming out, giving instead of carbon dioxide, that means depending upon the pH of the medium, you get the carbonic acid and NH3. So, this particular one, it can be when in presence of ammonia or in some basic condition, you can consider it as carbamate anion also. So, an is the intermediate. So, identification of this also was very crucial, that this particular species, either the carbamic acid or the carbamate, as intermediate, because whenever we are talking all these gases and all these molecules involving this carbon, nitrogen and oxygen in the typical cycle and the metal center, we always try to understand something, that whether this sort of species in nickel environment or in some metal environment, whether they can function as a ligand or not, because all these transformations and all these reactions, we are just talking something where you have the metal center and the ligand center. So, those two are interacting. So, this is not a very big molecule, it is also a very small molecule, having a molecular weight of say around 590,000. So, it has a molecular weight of and sometime it varies with another small unit of 30,000, and this activity, that means urease activity, is dependent on the presence of Ni, that means its activity is proportional to Ni2 plus content. So, it is not that is the not related to some organocatalysis, that some organic molecule and some Lewis acid interactions are taking place and you get the catalytic activity, but here definitely you need the presence of Ni2 plus. So, it is a metal centered catalysis, and a corresponding system what is present there, that what are the nickel environment. So, nickel environments are octahedral, and we have that slowly people have identified that you have so many histidine residues, and those histidine residues are attached to the nickel center, giving a octahedral geometry which is highly distorted. So, you have octahedral nickel environment, and around which some position is there such that the substrate, because we are looking for some hydrolysis reaction and you have nitrogen as well as oxygen. So, this is your urea. So, if we think of that this can function as a ligand, so it can be interacting with the metal center through oxygen lone pair or nitrogen lone pair. So, in this particular case, we will see that your metal center is bound with oxygen. So, this environment is also facilitating that is particularly there is some pocket. So, pocket, whether that particular coordination pocket will allow this particular end or that end. So, this particular end is a small end, and that end, that means this carbonyl oxygen can go and directly attached to the nickel center. So, what we have once this is reacting as a ligand, we get something which we can consider is as O coordinated ligand, not N coordinated. So, urea would be O coordinated, and this particular one, the nickel center will show some Lewis acid behavior. So, Lewis acid behavior will be shown by nickel, and basically it will drag the corresponding electron density from this oxygen, and the corresponding attack for the nucleophile will lead to the hydrolysis reaction. So, this the first step is that you have O coordinated urea, and the second step should be the attack of the nucleophile. Either it is the water molecule or the hydroxide anion. So, when we talk about that, we are looking for something where your urea is consumed and we are producing ammonia. So, definitely we are talking something which is directly related to the plant's nitrogen metabolism. So, it would be related to our very important reaction for nitrogen metabolism. In all cases, in plants as well as in microbes. In plants and microbes. So, this informations will not tell us that how many nickel centers are there within the system, but we should have some arrangement that one particular center, that means the same nickel center can function to bound the urea molecule as well as the nucleophile, if these two nucleophiles say water or hydroxide ion. So, water and hydroxide ion, either they are coming from the reaction medium or it can also be bound to the metal center, but the most efficient mechanism which we can have is that the presence of two nickel center. That means, here we are talking about a binuclear system. In case of iron and all other cases, people have now identified that the most effective arrangement for this reaction. So, one will be responsible for substrate binding and another will be responsible for the nucleophile binding. So, the water and hydroxide group bound to the second nickel will attack the substrate which is bound to the first nickel. So, the environment what have identified now from the structure also, X-ray structure, that these are water molecules, then we have nitrogen from histidine 272 and another nitrogen from another histidine which is 246, and on the left we have one water. So, we have two water molecules attached to both the nickel center as monodentate ligand. So, that is why people are initially confused that whether the same water molecule will attack the corresponding urea for the hydrolysis reaction, and also in unique bridging ligand water. Two more nitrogen histidine which is 136, this is another nitrogen histidine which is histidine 134, and this one is one oxygen from carboxy end which is aspartate. It is aspartate 360. So, altogether we have taken 1, 2, 3, 4, 5 coordination sites around this nickel and 4 coordination site on the other. And to support this dinuclear entity, so this is the monodentate coordination of single water molecule, and this water bridging is also very weak if it is not symmetric one also, because it is a very long distance. This water is a neutral one, not a hydroxide one or oxide one. So, we need some other support from this side, which is the carboxy bridging, and which is not a pure carboxylate group, but is carbimylated lysine. So, which is numbering is K217 and 1 star, because this is derived one. You have the lysine, and that lysine group you have the NH2 function, and NH2 function is reacting with carbon dioxide, giving that carbamylated lysine. So, these are some unique transformations in all these living systems, that if you have free NH2 end, or sometimes if you have in synthetic molecules, what we find that if you have RO minus, that any alkoxide group. So, this alkoxide group can bridge 2 metal centers like hydroxide and oxide. These also can bridge 2 metal center, but if in between you have certain arrangement, that if your pH is suitable and in a carbon dioxide environment, or if you can react with carbon disulfide, the bridging groups like RO minus and RO minus can be transformed to the corresponding alkyl carbonate ROCOO O minus. This also xanthate C double bond S minus. Okay. So, we were just thinking, or we are just talking that these simple groups can bound 2 metal centers, one metal center here, another metal center, or another metal center, but sometime presence of this carbon dioxide or any other group, these bridging groups can be transformed. So, if you have a free amino acid like lysine with NH2 function, and that NH2 function with the use of carbon dioxide, it can be converted to a corresponding carbamic acid type of arrangement, and that carbamic acid type of arrangement, basically this is the strong binding compared to your water binding, and these two can keep the nickel separation also unique for binding of your urea molecule and the corresponding attack from either this water molecule or its corresponding deprotonated one. So, it can go for immediate deprotonation also to give you the hydroxide bound nickel one, and it can attack the corresponding binding of the urea molecule to this center. So, this particular hydrolysis reaction, though it looks very simple, but it has some kinetic barrier. So, if you have a huge kinetic barrier for any reaction, basically that can be lowered by all these coordination and other thing. So, barrier of this kinetic reaction is for hydrolysis. So, kinetic barrier for hydrolysis is presumed to be lowered by the first one, which we just talked right now, that coordination of this carbonyl group of urea to one nickel, say nickel 1. And second step, if it is there, that means the corresponding binding of water which is be required for the nucleophilic attack. So, binding of water to the second nickel, not the same one, that is important. So, binding of water, that means when it is bound to water, it can undergo deprotonation and you can have some activated, it means is nucleophilic activity is increased, you have activated OH minus group in your hand for the reaction. And lastly, which is also very important, when you have the corresponding substrate, and this substrate we all know that the urea substrate is very interesting to understand the hydrogen bonding interactions. So, after all these coordinations, you still have some hydrogen bonding interactions. Because this O group is bound to the nickel center, but if you have the NH2 here, the NH2 here, and which are away from the metal side, and these two nitrogen this NH functions can be good hydrogen bonding donors. So, you have hydrogen bonding interactions of all 4 hydrogen atoms of urea. Interactions of all 4 hydrogen atoms of urea with some available electrophilic groups of the protein. So, protein will be responsible for suitable positioning of the entire urea molecule, not only to the metal coordination, but hydrogen bonding interaction with these NH2 functions basically trap the entire molecule close to that of your 2 nickel centers. Some groups of the protein, what we have seen in case of hydrogenases also, which is a cationic one, but still suitable positioning is allowed close to the metal site. So, if we have the nickel, so one nickel will be responsible for binding your carbonyl function, and these hydrogens will show hydrogen bonding interactions with some other groups of the protein envelope. And the second nickel center will have the OH group. So, this will attack this carbonyl function, because we just go for electron push to the metal center, and as a result we get some intermediate, because this intermediate, when this OH is attacked, this carbon becomes tetrahedral. So, we have O, and this is the attacked OH, so this one to first nickel, and this one already bound to the second nickel, and these lone pairs are available. So, it can take up this as a proton, removing one ammonia molecule, and this particular one, even for if the system also gives one proton. So, this can be either NH2 or NH3 plus. If it takes this proton, so you have in one particular site you have the carbamylated lysine. So, you other end you also see something the same type of arrangement, that bridging groups from this thing. That means what we are looking for, the product formation for hydrolysis of the urea. So, this ultimately is responsible for the removal of the second molecule of ammonia when your H2O is attacking. So, at this particular point you have NH3 plus H2CO3. So, the interesting part for this is that you have the corresponding support, that means a similar type of arrangement, this carbamylated type of arrangement which was there on the other side of the nickel. So, the thing is that you have the nickel environment and you have the corresponding bridging groups on this side. So, this nickel center is there and this nickel center is there. So, other side also the similar arrangement is taking place. So, initially within the ligand system, whatever groups are present, that means a weakly bound water molecule which is loosely bound as well as the another monodentate water molecule, all will go. So, basically the enzyme is resting on an acetate bridging moiety. So, in this particular one, because the enzyme is a very big molecule and whatever thing we should think of, that means if we just talk about some model chemistry or synthetic chemistry related to this, that if we can get this particular arrangement, that means for getting the arrangement for copper acetate, all we know these are the very standard example and well known example, but still we do not know all the time, we do not care all these things. So, this copper acetate monohydrate which is basically a dimer, and when you have two copper center like these two nickel, what you get? You get 4 bridging acetate groups. So, these 4 bridging acetate groups are basically responsible for the stabilization of a binuclear entity. But in the protein environment, what we are talking about and what we are discussing, that when you have this, when the substrate is coming and binding to the nickel center as well as your nucleophile is binding to the second nickel center, the entire thing within the protein envelope is supported by only one acetate type of bridging, which is very difficult to get, because you may argue that why we are not getting one particular arrangement, that all other ligand positions you can change starting from simple copper acetate. So, you remove one acetate first by some other donor group, you remove the second one, you remove the third one, only I will remain with the dinuclear arrangement with one acetate bridging, but that is not so easy and it is also impossible. But in this protein environment, that you get something where your one side is bridged by the acetate group and whatever substrate, that means that corresponding driving force for going for this sort of substrate, that means this bridging entity is also supporting this dinuclear entity, because on the other side this bridging is forming. So, as the intermediate after removal of the first ammonia molecule, before the removal of the second ammonia molecule, whatever arrangement you can have, that means in this side you have this already carbamylated bridge and the other side you have the substrate, the transformed substrate bridging. So, this particular type of arrangement is still there and which is a stable arrangement. So, all these things will give something that you just go for the corresponding rate of transformations, and the corresponding kinetic parameters are also very high in number, and we get immediate evolution of this ammonia molecule and all this. So, the second one, this is the first one, The second one, which is a very important one for some important reactions like hydrogenases. So, once we get that urease, the second one based on nickel. So, nickel enzyme will be useful for hydrogenase reaction. So, there we are handling carbon dioxide and ammonia. Now, we are talking about the hydrogen gas. So, all these gas phase reaction, and that particular reaction will be just simple, though it is a very simple reaction, and in terms of our energy demand, how we make this simple reaction. So, is a redox reaction now, the difference with that of urease, and we still use the nickel center. So, is a 2 electron redox transformation for production of hydrogen from proton, and E 0 prime is minus 414 millivolt. And for this particular arrangement, we not only need nickel, but one well known system is based on iron and sulfur. So, there are several other hydrogenases. So, large number of hydrogenases are known. There are some hydrogenases which bears only iron and sulfur. So, they are only iron bearing hydrogenases, but when we talk about nickel enzymes, so nickel will also be present along with iron. So, it will be nickel iron sulfur proteins. And not only they are useful for the reactions of hydrogen production from the proton, because it is highly negative potential. So, we need some corresponding difficult reaction for the electron transfer to the proton. So, not only hydrogenases, but also this sort of molecules, that means the nickel iron sulfur proteins are also useful for carbon monoxide dehydrogenases. So, we will see one after another slowly, and they are abbreviated as CODH. So, again after ammonia, after carbon dioxide, after hydrogen, we are talking something again another gas molecule. So, you see all these things, because most of these cases, because all these nitrogen proteins and nickel proteins and nickel enzymes are useful in some anaerobic condition. That means, we do not need oxygen for all these transformations. So, these hydrogenases, this one can be considered as, we will just within square bracket we will write it as nickel iron hydrogenase. There are one type which is Fe hydrogenase. That means, when you write Fe hydrogenase, that means at least 2 metal centers you require. So, whatever we are talking, all these proteins, they are binuclear. So, we need 2 metal centers, and sometime only one iron center is also sufficient for hydrogenase reaction. So, one such is after hydrogenase, the similar nickel iron sulfur protein is useful in carbon monoxide dehydrogenase, and another very important reaction that we will discuss in our next class is acetyl coenzyme A formation. Acetyl is nothing but how you make the acetyl function from carbon monoxide and carbon dioxide, because we are talking something that how we get organic molecule through these biological pathways starting from either carbon monoxide or carbon dioxide. So, acetyl function you can synthesize. So, acetyl coenzyme, these are coenzyme basically, not co-word. So, coenzyme A synthase, because it is responsible for the synthesis of acetyl coenzyme A. So, let us first see about these hydrogenases. So, these hydrogenases are bearing nickel and iron. So, basically is a very unusual one also. Unusual nickel iron active site. So, both the iron site as well as the nickel site will be responsible for the reaction. That means, you have to have some arrangement, whether you have the corresponding heterolytic cleavage of the hydrogen atom or some homolytic cleavage of this hydrogen atom as the hydrogen molecule as hydrogen atom, and those groups basically how they are going to bound to the metal center or some other groups nearby to those metal centers. So, first of all we have to identify the groups which are binding our two metal center, that means nickel as well as iron, and the identification of their oxidation states. So, in the resting state both the two metal centers for these is +2 on nickel and +2 on iron, and that unique bridging groups are sulfur. So, that is why it is nickel iron sulfur protein. We know all about the iron sulfur proteins, the ferridoxins, the rubidoxins and all other. So, it is also a nickel iron sulfur protein, because you have the sulfur and this sulfur end is coming from the cysteine residue. The cysteine residue with sequence numbering is 495 and cysteine 73. So, they are quite apart. So, if it starts from here, so it goes and the other side it is then ultimately coming at 495, and here the other two positions, one is again cysteine and which is cysteinate 70, and other is sometime sulfur from the cysteine residue, and in some other cases it is selenocysteine, that means selenium function is there. So, selenocysteine residue number 492. Some molecules it is selenium, which is very much close to sulfur. So, this particular environment, that means this side, so you have nickel in a typical sulfur environment. That is why during the last 25 years or so, people are investigating so much about the corresponding coordination chemistry of nickel in typical sulfur environment, that how many sulfur environment you can have, whether sulfur is typical S minus or thioether sulfur or thioamide sulfur or any other thiourea type of sulfur. So, if you have the different sulfur groups attached to the nickel center and people just simply tried for that, the typical reaction in the model chemistry, that how many of these in sulfur environment can go for either corresponding a typical loss of electron, that means either it can go for +2 to +3. Okay. So, when you go for oxidation, that means whether your sulfur environment can support the oxidation of the nickel center. So, people make some different types of ligand system, make the mononuclear compound, because initially the challenge was how you find out this particular mononuclear environment, though it is a part of the binuclear system, but it is a mononuclear environment, how it is behaving if there is something which is the redox reaction, because this is a typical redox catalysis. We have to supply the number of electrons to the proton center, and if you have some proton pool, that means H plus is there, and interestingly we will find that some of these H groups can also be bound to the cysteine residues, because one such good example for the ligation for this nickel center is the cysteine sulfur, that means S minus. So, your S minus can be a very good ligand. if you go for the corresponding alkyl group, that means the S-methyl function, that is also a very good ligand for you. And sometime you can go attach some carbonyl function and then S minus, this is also a very good environment for sulfur. Then you can, just now I told you the way, that is you can have the corresponding xanthate as the environment, then you can have N diethylamine which can react with these sulfur groups to give you the dithiocarbamate functions. So, these are some sets of all these molecules what can give rise to some coordination chemistry for nickel in sulfur environment. And what people can do, that for the oxidation as well as the reduction reaction, you do not know what is there, because sometime we will see in this catalytic function that you have to support all three oxidation state. So, your nickel environment is such that you can go down to nickel in the +1 oxidation state, or you can go up to nickel for +3 oxidation state. So, during this turnover, this catalytic turnover, if you just simply go for this, the way we got, you think it clearly that in case of iron or in case of copper, during the dioxygen activation in hemocyanin, we get the reduced form. Then immediately you transfer both the 2 electrons to the corresponding antibonding orbital of the dioxygen molecule, and you transform the dioxygen molecule from dioxygen itself to peroxide. So, those electrons are basically we are feeding to the dioxygen molecule in its antibonding orbital. Now, what we are doing? We are doing nothing, but we are pushing those 2 electrons to the protons. So, basically supplying those electrons to the protons will ultimately lead to the hydrogen production. So, if you just simply go from here to there, that means if you just can make some thing where you have the nickel in +1 oxidation state, immediately you can go to nickel +3 oxidation state, you get 2 electron out of this. So, this 2 electron transfer is possible, and those 2 electron transfer will be required for utilizing your reduction for the protons to hydrogen molecule. So, in this environment, what people did for this, all these ligands, different types of ligands, sometimes with the combination of nitrogen donor as well as oxygen donor. So, you make the synthetic molecule and you determine the corresponding E0 values by simple technique like cyclic voltammetry. So, cyclic voltammetry will tell you in the next step the how easily, what are the corresponding E0 values, how easily you can go from a nickel 2 plus compound, a bivalent nickel compound, to a monovalent nickel compound or a trivalent nickel compound. So, you determine these E0 values. So, the knowledge of these E0 values will tell you how easily you can go from one oxidation state to the another, how easily the other 2 oxidation states are accessible from bivalent nickel. And also some spectroscopic technique like electron paramagnetic resonance, EPR is useful for identifying the formation of nickel in +1 oxidation state or nickel in +3 oxidation state, because this is not EPR active, but this is EPR active and the trivalent state is also EPR active. So, all these chemistries, a little bit you can study also, that the corresponding coordination chemistry in all sulfur nickel environment, which is very important, and from all sulfur nickel environment you can go for a binuclear entity also, because if you have this S minus, that means charge is more on these groups. So, if you have the cysteine sulfur over here and it is neutralizing the nickel, so you have 1, 2, 3, 4. 4 negative charges are there which are not sufficient for going for this corresponding charge neutralization on the nickel 2 plus. So, either it can go for a oxidized form in the +3, where the charge, overall charge on the complex would be less if you go for the oxidized form, or this sulfur can be used for bridging the second metal center. That means, this particular group, these ligand groups will have some tendency to bridge the second metal center. So, these cysteine sulfur. So, why these cysteine sulfur? That means, why these two sulfur groups, the cysteine sulfur groups are different compared to this sulfur which is in the terminal position. So, iron site you get, so these two cysteine sulfur residues are attached to this particular nickel site, and you have 3 other groups which are attached to your iron site. So, these are now very unique, which is not known earlier in any living system, that these are CN, CO and CO function. So, these are typically non-protein ligands. So, whatever inorganic chemistry you are doing in the laboratory, we see in the living organisms also. So, these 3 ligands CO, CN and CN, they are therefore non-protein in nature. So, they are non-protein ligand, which is a very unique system for this sort of molecules. So, whatever we are talking is the protein molecules, but the ligands are of different origin. So, they are carbon monoxide, they are CN and the another carbon monoxide. So, they are non-protein ligands, and these ligands all we know from the typical coordination chemistry knowledge, that they are responsible for stabilizing the metal center in low oxidation state. So, they are all pi acid ligands, we all know. So, these 3 ligands basically restrict the iron center in +2 oxidation state. So, they basically maintain the iron site in +2 oxidation state. So, once you know, because if you know the basic structure from in this fashion, that means identification of all these positions around iron will immediately tell you that where from you basically get the redox activity. Whether this corresponding redox activity, you know both the metal centers are redox active, whether you get the corresponding redox activity from the iron center or the corresponding redox activity from the nickel center. So, once you stabilize or just block this corresponding center in the +2 oxidation state, that means this center cannot go to +3 oxidation state. So, definitely whatever redox activity related to the reduction of the protons we should get from the nickel center. So, nickel center will definitely supply the electrons for the reduction of all these protons, it is not the iron center. So, that we will see in our next class, that how the catalytic cycle is operating in that way. Okay. Thank you.